Hi, this is Dr. Joseph, and we're getting ready to record the final two videos of the year. Okay, our last topic is polar coordinates. So you may have dealt with this in a previous class, but just to remind you of some things, there's some neat background here that this was introduced by Isaac Newton. Um, and let's see why it's more convenient for certain kinds of curves. Okay, so we have an origin, some point in the plane, and this ray here we call usually the positive x-axis, but right now this is the ray corresponding to the angle 0. Um, and then the other angles um, are all represented by a ray coming out of the origin, and a particular point in polar coordinates has a radius and also an angle associated with it. Um, so of course, any point can be written this way. Um, what's different about this versus rectangular coordinates is that it's not a unique representation. Um, so for one thing, the origin um, certainly has a radius r of 0, but its theta can be anything we want. And that represents the same point. So 0 comma anything is the origin. We can also allow r to be negative. So here's the point r theta. It looks like theta is maybe pi over 3. Um, if we keep theta as pi over 3, but replace r with negative r, all this does is take us into quadrant 3 along this line to the opposite point here. So this would be the point negative r with the same theta. So you might say, why do that? Well, it turns out to be convenient when graphing equations. So we'll look at a more explicit example of that in a moment, but that is an important thing to remember, that negative r theta is the same as positive r, and then adding pi to the angle. Two different ways of writing the same point. Okay, so here's an example. Plot a few points. Um, I think I'm even just going to do a couple of these and let you do the rest. So remember the the polar coordinates always go r first and then theta. So radius of 1 means we're on the unit circle, and an angle of 5 pi over 4 is here. I'm going to assume that this first circle has a radius of 1, so then that would make this the point 1, 0, and then 2, 0, um, etc. So then 5 pi over 4 and a radius of 1 would be right here. So that's our first point. And then radius of 2 and an angle of 3 pi. Okay, so 3 pi is 1.5 revolutions. So it's the same as saying an angle of pi, and a radius of 2 would be right here. So that'd be our second point. Um, and I'll let you figure out the rest for yourself. So negative 2 pi over 3, that means we're going this way by 2 pi over 3. Um, and negative 3 pi over 4, that means you find the angle 3 pi over 4, which is right here. And then negate that, so that'd actually be on the opposite side. So you just follow that line, 3 units. Okay, so I think that's a good warm up. Um, yeah, so as we said, we can always negate r if we add pi, and then adding a multiple of 2 pi never changes anything to the angle. So you can add any even multiple of pi to theta and keeping r the same, or if you negate r, you can add any odd multiple of pi, and those all represent the same point. Okay, so this slide is very helpful because it has a way to convert between the two coordinate systems. So Cartesian, X and Y, rectangular coordinates. Um, that's what we're most used to. And in that in that system, we can just draw this right triangle and figure out that X is r cosine theta and Y is r sine theta. Um, Now, if we're given the Cartesian, the x, y, and we want to convert that to polar, of course, there's many possible answers, but one possible answer is to have r as the positive square root of x squared plus y squared, and theta as the inverse tangent of y over x. Um, so you may not remember, but the range of the inverse tangent function is quadrants 1 and 4. It's negative pi over 2 to pi over 2. So this will be correct when theta is in quadrant 1 or quadrant 4. And this note that we sometimes have to add pi um, is for when theta is in quadrant 2 or quadrant 3. And as usual in calculus, we should be using radians, not degrees. Okay. So let's see, convert the point 2 pi over 3 from polar to Cartesian coordinates. All right, so from polar means that this is r, this is theta. So x is just r cosine theta, which is 2 cosine of pi over 3. Cosine of pi over 3, well, sine of pi over 3 is root 3 over 2, so that's 1/2. So 2 times 1/2 is 1. Y is r sine theta. So that's 2 times root 3 over 2, which is just 2. So my x, y Cartesian coordinates is just the point 1, comma 2. Okay, represent the point with Cartesian coordinates 1, negative 1 in terms of polar. Um, so now it's good practice to use these formulas, but another thing you can do, especially with a simple, relatively simple point like 1, negative 1, is just graph it and then figure out what are valid polar coordinates for that point. So that's going to make an angle of 45 degrees downwards, so negative pi over 4. And the hypotenuse there would be a length of root 2. So this is one possible answer. Okay. Okay, so when we talk about graphing an equation in polar coordinates, It may be of the form r equals f of theta or f of r theta equals 0. So it's an algebraic expression involving r's and thetas. Um, the definition of that is that it consists of all points that have at least one polar representative um, satisfying the equation. So r equals 2 is just going to be a circle of radius 2 centered at the origin. And again, using our conversion that r is square root of x squared plus y squared equals 2. That's equivalent to the Cartesian formula for the area of a circle with centered at the origin with radius 2. Um, so that's A. And B, sketch the polar curve theta equals 1. So that means 1 radian. Um, so 1 radian is roughly 57 degrees. So would look something like that. Now, this ray I've drawn is where r is positive. So here's where we have to remember that we need to allow for the case that um, r is negative. So for example, the point -3, 1 in polar means I still have an angle of 1, but I'm on the other half of the line. So it'd be a distance of 3 going into quadrant 3. Um, so the full graph then will actually be this entire line. And getting back to that formula we had, that theta is inverse tangent of y over x, there's a nice way to find an equation for that line very quickly. Um, so this means that tangent of theta equals y over x. Y over x, that's my rise over run for my line, my slope, right? So in this case, so that would mean that the equation for that line, because it's definitely going through the origin, is just y equals tangent of theta times x. In this case, it'd be y equals tangent of 1 times x. Tangent of 1 is roughly 1.56. So that would be an equation for the line. All right, so let's do a couple more examples. Sketch the curve with polar equation r equals cosine of theta, and then find a Cartesian equation. So switch it, convert to x's and y's. So for problems like this, I recommend making a table with some values. Um, it's a little funny that we do it in this order because theta is the independent variable, but we're writing it second. So just have to remember that. But let's just put down a few angles that we know off the top of our head. So 0, pi over 6, and see what happens. So cosine of all those angles, cosine of 0 is 1, So that means I'm starting off at the point 1, 0, which it, funnily enough, has the same coordinates in polar as in Cartesian coordinates. Um, Cosine of pi over 6 is root 3 over 2. I will find a decimal for that in a moment, but let me just run through this list here. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. And then cosine of pi is -1. Okay, so all right, so I filled in some of those values and I'm gonna graph them. So I'm going to sketch these angles first. This is pi over 4, pi over 6, and pi over 3, pi over 2, and pi. Okay, so when theta is pi over 6, I should have a radius of 0.87. So if, um, yeah, little bit less than the unit circle, maybe right there. And then pi over 4 is 0.71. So even smaller. And then pi over 3 is a radius of 1/2. And pi over 2 is a radius of 0. So that is the origin. And then this is a big jump, but when we get to an angle of pi, my radius is -1. So the point -1 pi in polar is the same as the point 1, 0. So I get back around to here. And I could draw a few more points, but I think where cosine is periodic, maybe you'll agree that um, in between pi and 2 pi, I should get the same points, but with negative y value. So the graph here is actually going to be a circle. Um, and let's prove that by converting to Cartesian. So this is not always an easy thing to do, but in this example, it's not so bad. Because r is equal to the square root of x squared plus y squared. Um, and this equals cosine of theta. Okay, so the other thing I know is that x is r cosine theta. So I'm going to actually just forget about this for a second and multiply both sides by r, and I get r squared equals r cosine theta. And now substitute for x's and y's. So square root of x squared plus y squared is going to be x squared plus y squared on the left-hand side, and r cosine theta is x. So that was a little trick that saved me some trig stuff. And now this is, well, I guess I could just say I'm done right here. This is an equation with x's and y's. Um, if you wanted to see that it is a circle, you would have to get the x's and y's on this side, and now we'd have to complete the square. So I'm actually going to have to add a quarter to both sides so that this factor says, oops, x minus 1/2 squared plus y squared equals 1/4. And that means that my center is 1/2, 0. And my radius is the square root of 1/4, which is 1/2. And I think from the sketch, that's pretty believable. The center is 1/2, 0, and the radius then is 1/2. Cool. All right, sketch the curve r equals sine of 2 theta. So this is not going to be a circle. And we're going to do more table. Let me just pause this while I get this going. Okay, so we have to double these angles and then plug them into sine. So sine of 0 is going to be 0. Sine of pi over 3 is root 3 over 2. Sine of pi over 2 is 1. Sine of 2 pi over 3 is root 3 over 2. Sine of pi is 0. Sine of 2 pi is 0. Sine of 3 pi is 0. And sine of 4 pi is 0. So I don't have a whole lot of points that are telling me new information there, but that is actually going to be useful. So let's see if we can sort this out. So we're going to start, I'm going to pick a different color here. Start at the origin 0, 0, and 0, pi over 2, 3 pi over 2. Okay, so let's draw those angles again. Pi over 6, 4, and 3, just approximately. Okay, so I start at the origin, and then my angle, or my, at pi over 6, my radius is root 3 over 2. So if you believe that this is continuous, which it should be, because sine is continuous, then that means I have to start at the origin and get to a point that's like here. And then um, that's a little bit less than 1. So I keep on coming out, and sine of pi over 2, that's the maximum value of sine of 1. So that's a radius of 1 right there. And then it comes back to where it was here in terms of radius. And then at an angle of pi over 2, it comes back to 0. Okay, so that uh that completes one loop. Now, as we range from pi over 2 to pi, that same sort of thing is going to be happening, but let's think about the graph of the sine function. Well, sine of 2 theta. Um, I'd rather think of this as sine of theta and just double it. So think of this as sine of theta as we range from pi over 2. Yeah, okay. So if, one second. Okay, I think I've got it. So as theta ranges from pi over 2 to pi, 2 theta ranges from pi to 2 pi. This is where sine is negative. So that means my r, which is sine of 2 theta, is negative. Um, for those thetas, which means instead of seeing the graph over here, you're going to see it over here in quadrant 4. So I came through, and then the same sort of pattern of radii will occur, but in quadrant 4 now. Kind of like that. Oh, never satisfied. Here we go. That looks good. Okay, sweet. So now that completes a second loop, and we can see as theta goes from pi to 3 pi over 2, then 2 theta ranges from 2 pi to 3 pi, and that means my radius is going to be positive in that range of thetas. So that means the graph really will show up in quadrant 3. So I did the first loop, did the second loop. Now the third loop is going to come like that. And you could probably guess R will be negative again for that uh, fourth range of values from 3 pi over 2 to 0. And we will end up looking like this. And then the graph would repeat after that. Okay, so that we can call a 4-petal rose. If you change that 2 into another number, you'll get a lot of other interesting looking graphs. Um, in fact, why don't we look at Desmos for a second? So this is a graph of sine of 2 theta. And if you're a little bit clever with Desmos, you can get a point to travel around. Let's make it a little bit bigger. All right, so my little purple point there is going to travel through a range of 0 to 2 pi. And that's what we expected. Great. So that's a good example. Another example I wanted to highlight is sine of 3 theta. And I've just the graph is going to be this 3-petal rose. I've split it up into um the various uh intervals of theta that make the different petals. And here we really only go from 0 to pi. And from 0 to pi over 3, you get this red petal. From 2 pi over 3 to pi, you get this black petal. But look, there's nothing here in between pi over 3 and 2 pi over 3, and that's because that's exactly where sine of 3 times those angles is negative. So r being negative there flips the petal down um, below the x-axis. And this is an example of why it's important to remember that we want to allow r to be negative. If we said we only want r to be positive, it would be a lot harder to write an equation for this. We'd basically have to do a piecewise function. Um, so that is important to remember going forwards. Okay, and I think we have, oh no, that was the last example. So that's it for this video. See you next time.